morning, good afternoon, good evening, from which other part of the world you are. Welcome to our 52nd webinar. Today we have with us Mr. Rahul Sharma. Mr. Rahul Sharma is the Joint General Manager, Design at National High Speed Rail Corporation, and is a civil engineer with 16 years of experience in hydropower and high speed rail infrastructure. For in the past, he held the position of manager of civil design at NHPC. He specializes in design and analysis of underground structures, including pressure tunnels, caverns, and NATM tunnels in complex Himalayan and Western Ghats terrain. His key projects include Makdechu HEP. Uh, at NHSRCL, he leads the team of water supply and firefighting network for the Mumbai Ahmedabad High Speed Rail. He is also a chartered engineer, and he is an active member of ISRM, TAI, and ISRMTT, and holds IPMA Level C Project Management Certificate. We welcome you, Mr. Sharma, to our webinar platform. Over to you.
Thank you, Rishi, for your introduction, and good evening to all of the listeners in the platform of TAIY. Thank you for giving this opportunity to share the insights on the tunneling infrastructure on through this platform. So, Rishi, one thing is that before starting, if there is any glitch of my sound because of the network issue or presentation, please just ping me on that matter. Okay, so that anyone will
Yes.
not miss the any kind of information. So now I am sharing my screen to all the participants. I think screen is visible now completely to all of them.
Yes, Mr.
Okay,
Sharma.
thank you. So I'm sure this tab will not disturb you. You can share, you can see my screen completely, or you will find one tab on the screen.
We can see it completely. We cannot see the
Okay,
secondary tab.
okay, that's good. Just a minute. So again, good evening, good morning, and good afternoon from the every part of the world. So this is the topic I want to deliver in this platform to all of the listeners, which is basically a high ground stresses and its case study. Why I'm choosing this topic? Because many of them will talk about the FEM and so many things will be going in underground. But basically, we are concerned about the input. And I am framing this presentation in that manner so that everyone in the listening team will get existence from the this information so that either it's from the site personnel or maybe from the design personnel, it's a starter or beginner or intermediate, at least they will assist in the better information of the high ground stresses, which is basically one of the critical input parameter in underground structures. So I will move ahead and its screen is changing, Rishi, because what I found the screen is not changing from my end.
Yeah, it's not actually changing.
Yeah, that's why I'm just a minute. Yeah, now it is changing.
Yes, yes.
I'm sure. So again and again, so why it is switching? I'm sure the tab of top is not disturbing anyone. Oh, now it's okay.
It's not.
So this is basically the intent which I am covering under this scope. The one is the basically the ground stresses, the basic theory about the ground stresses, in situ stresses, and induced stresses, and then we'll move ahead with the rock stress classification, and then the response of the ground under these stresses condition, and then the ground support, and few international case studies that how they tackle these situations under these problems raised under coming under high ground stresses, and then ground management theories. This is basically the ground stresses which you are just feel on my screen, and in which you see that the basically the ground stresses. Sometimes there is a lot of confusion in the industry that what is in situ stress and what is ground stresses. So I am just talking from the scratch side, that whenever we are making any kind of underground structures beneath the ground, that we are basically catering with the two kind of stresses. One is a near field stresses and one is a far field stresses. So if you see this figure, which I'm highlighting my pointer, the basically these complete pressure which is coming as an overburden pressure is basically a ground stresses, which sometimes we can term invariably as a in situ stresses. So it will be having a basically three part: the vertical stresses, horizontal stresses, and intermediate horizontal stresses. And if you define in the matrix form, it will be a well-bore coordinate which will be defining in a matrix, rotational matrix basis. So if you find this figure, you will find that whenever you are making a boundary, here will be the near field stresses will be developed, which is in a radial and tangential direction along the tunnel boundary. So basically, the complete ground stresses is divided into two parts. One is a near field stresses and another is a far field stresses. So whenever we are disturbing the ground, so boundary which is basically is disturbing coming under the influence of this formation of tunnel is called as a far field stresses. And exactly the boundary, the ground and the tunnel cavity, it's called near field stresses. And then these both stresses coming as in ground stresses or in situ stresses. Now the next will be, I think there is a network issue.
It's visible. Uh,
Yeah, next slide is visible.
no,
No, that is the point. Actually, I am
slide.
not. Yeah, yeah, just a minute.
Accessibility shortcuts.
Yeah. Maybe I think there is an issue with the network when I'm stucking. Maybe okay. Sorry for interruption. Again, I'm continuing my work that the in situ stresses. We are talking about the in situ stresses. So if you can see my screen, the basically as I already told you in my previous slide, that basically the in situ vertical stress and in situ horizontal stress. So if you see these pictures here, you see the completely the basic theory of this overburden pressure is termed as gamma z. Basically is the in situ vertical stress, which is you show in the sigma z, and these two stresses, which is basically sigma x and sigma y, is our in situ horizontal stress. So basically it's very easy to say the in situ stresses with overburden stresses, but sometimes when you go in a mountainous region, the more critical conditions become in situ horizontal stresses. So the basically we have to be just keep in mind whenever designing the underground infrastructure, that what will be the stress regime inside the ground. That is what is basically the overburden stress as well as the horizontal stresses, which will be developed due to the tectonic section. So these horizontal stresses are also equally important as compared to overburden pressure when you go in a high mountainous region, because that is one of the principal parameter to design what will be the alignment of our tunnel. So if you see, this is the question why we are saying that these are the important, because when you are making any kind of a cavity inside the mountain, then you will find if there is any stress regime exists in the equilibrium condition. When you're not making any cavity, that means there is no issue. But if you're making any cavity, then your stresses will be mobilized. And if these stresses is not mobilized adequately, then definitely it will be going again in a compression mode and will try to destabilize your tunnel or cavity. So this is one of the question become very important, that apart from the ground stresses, in situ stresses, how you manage these induced stresses. And now question comes, what will be the induced stresses? So it's a basically, it's in simple terms, it will defined as a anthropogenic stresses which is developed due to the removal of the natural material by your excavation techniques. So you have to be very careful that in what way you are excavating the ground and how you are managing the induced stresses, because The balance between the ground stresses and induced stresses is most important to managing the any tunnel cavity inside the mountainous region to stabilize these structures. Now the question comes that how we define these rock stresses. So it's one of the work which is done by the Balestine and Barron in 1971. In work by 1971. Rushi, is my screen visible to you?
No, yeah,
Now
now
it is
it's
visible. It is again and again going back to back. I'm not sure why it is happening, but okay. Uh, Now it is visible
yes,
and without any hindrances on the screen.
yes, the full
Yeah,
screen
that's
is
great. Now, next is the rock stress classification. So if you see the rock stress is basically divided into the in situ virgin stresses, which is I already explained the term called ground stresses, and the another the induced stresses, which will be developed when you do some kind of mining, excavation, pumping, injection, energy extraction, and applied load and swelling. So these are the two terms which basically broadly define the rock stresses. And if you again go into the virgin stresses, it will be having a four component: the tectonic stresses, which is basically due to the development of the plate tectonics. Then the residual stresses. Sometimes in FEM we put the residual stresses, but what will be the residual stresses? So it is completely about depend on the how these rocks will be formed. It's a igneous rocks, sedimentary rock, or metamorphic rock. So it will be having a certain procedure of diagenesis, metamorphism, magma cooling. So basically, these residual stresses is basically depends on the formation process of these rocks. And now come next is a gravitational stress. So it depends on the topography. It's simply termed as an overburden stress. And next one is a terrestrial stress, which will be developed due to the pulling action, seasonal variation, rotational effects, and diurnal stresses. So this is all are basically classified under the in situ stresses. Now the next one with the active tectonic stresses. So if you go into the active tectonic stresses, you will find there is a some terms. It's basically more technical in terms of the physiology of the structure as compared to civil engineering part. But yes, we should know that what will be the actions will be going in a ground. I am sure the geologist is always be good in terms of explaining the but as an engineer on the ground or on the design, you should know that how these structure detailing will be going on. So it's a shear traction, slab pull, ridge post, tense section, membrane stresses. This is a broad scale. And if you're having a localized, that's why if you do any kind of analysis or any kind of topographical study, you should know the regional geology, because the regional geology is impacted by these kind of terms. And the last one with the remnant tectonic stresses. That means if you are in any kind of seismicity zone where you will find some kind of seismicity is there, then the thing is that you should be capable to know that what will be the seismicity of this structure. I think I will just drop my camera and then we'll start. Maybe it will good for all of us. Yeah. So this is basically the remnant tectonic stresses. So it's basically defined the same as residual stresses, but tectonic activity is involved, such as jointing. So our jointing, faulting, and faulting bondage in the ground is basically outcome of these tectonic stresses. So the next is the rock mass response. So now this has become a principle. What we discussed in the previous slides, it's basically that how the rock mass will behave under these ground stresses. So we can discuss the following terms in terms of rock mass stress, the basically ground stress, in situ stress. But in these conditions, how our ground behaves, it will be coming under this slide. So actually overburden depth, whether it's height of NZ, H or Z, whatever term we can use, it's basically stress related problem, which is basically function of the following parameters. So the whole concept of these stresses is divided into the three conditions. One is a local pre-existing stress field. That means whatever we are doing, either mining or excavation, that how induced stress will develop. That means how radial stress will travel and how tangential stress will travel. And that will define your plastic zone as well. Now, the second one is your the rock properties. That means in which rock you are working on it. It's a whether basalt, quartzite, phyllite. So what type of rock type it is, and it's what will be the strength of these and its index property like density, porosity, sonic velocity. So these all one and two is a function of your stress related problems. And the third part is discontinuity. Sometimes it will be clear in the mind that rock mass is basically the intact rock plus discontinuities. So the properties of the discontinuities, joint strength will be very important to assess the stress related problems in the ground. And if we summarize these graph which I am presenting right now, then you will find that to predict the behavior of rock mass adopted for excavation and mining activity, its strength and index property, which is basically its inherent property, details of discontinuity present, that is the nature which develop discontinuities inside the rock, and the other external factor like environment and surrounding. That means how stresses in travel because of the plate movement, because of the certain environmental impact. So these completely give the information that how your rock behave when you're doing any kind of disturbance into the rock. So this is one of the very great work, and I must say that apart from this presentation, when you go the on YouTube and see the recording, please just refer these references because I clubbed from the multiple books and references, and it will give a very nice work in the rock engineering in terms of the high ground stresses. So if you see in this work, you will find there is a one work, there is a one graph which is developed by the different failure modes in Kaiser and came in 2008, and they will define the two phenomena. One is a strand burst, which is basically rock burst, and second is rock squeezing. And how these two phenomena will work, I will just later on discuss. But first, we discuss with the failure mode. If you see this graph, you will aware about the term RMR, the rock mass rating. And the next one is a sigma 1 upon sigma c. So this is nothing. Sigma 1 upon sigma c is basically sigma 1 is basically in situ stresses along the boundary, and sigma c is your UCS, the uniaxial compressive strength of the ground. That means either it's a basalt, phyllite, and every kind of rock, it will having a certain properties, which is basically the index property of that ground, and which we done in a laboratory or something. And sigma 1 is basically the disturbed stresses which develop due to your excavation or mining activity. So when you see this picture, you will find that as your RMR is increases, your RMR is reducing. And as your RMR is reducing, you will find that chances of failure will be also increasing. So he will divide it the three zones. One is a low in situ stress zone. That means sigma 1 is 0.15% lesser than is your sigma C. Then these are the three conditions will rise. In these condition, you can manage by providing some kinds of proper rock support, bolting and something, because your response will be the either linear elastic response. Here your blocks will fall, then you have to do the spot bolting and unraveling. So you will do the short plating. In case of intermediate, you can know the stress regime. Then only you can decide your alignment, because this is not only for the rock support. For deciding your tunnel alignment, this is also very important, that what will be the stress regime in your structure. So if you go in intermediate in situ stress, you will find the sigma 1 upon sigma c ratio will be varying between 15% to 40%. So it will creating a such kind of influence. And this is, if I am explaining in that way, that this is the stress block. And if you are pressing from the big arrow, which will be having a higher sigma c, then your failure zone will be developed in that manner, which will be a brittle failure, and it will be creating some kind of rock burst situations. The most important and most critical, which will be better to avoid, if you not, then definitely you will having be ready with the heavy protections or heavy support measures, which will be the high in situ stresses. So when we go in a deeper in the mountainous region, more than a kilometer, then you will definitely coming into this zone, and it will be nothing but it will be a sigma 1 upon sigma c greater than 40%. And in this case, you will find if it's a massive RMR, that means RMR greater than 75, which you will find lesser discontinuity. In this case, you will be ready for the rock burst condition. But just the opposite in the case, if you find highly fractured zone, then definitely it's a kind of squeezing situation. So in these both the extreme condition, one is in basically high massive rock and high in situ stress condition, then you will find rock burst and rock strain condition. And the second one is in squeezing condition where your rock is competent, but because of the fracture reason, it's reducing its strength and quality. So this is the what I discussed. And if I'm going little fast or anyone having any issues, please poke me so that I can reduce my speed if you feel that I'm going little fast. Rishi, it will be okay, the pace which I am maintaining right now?
Yes, sir. It depends
Yeah,
on you,
that's
sir.
great.
Now
Yeah.
it's fine.
So this is what we discussed in the previous slide. This one, the outcome is this one. So what I am discussing, it's better to represent in a pictorial manner so that everyone who will not acquisition will know what I am trying to say. So if in a ground high stresses, when we are going in a larger stress conditions, there's a two kind of situations. If it is a hard rock, what I am discussed in a uniaxial compressive strength and in situ stress, then it will be a chances of strain burst. It's a multiple term. It's a strain burst, rock burst. It's, we can say, multiple terms. So the picture at the bottom, you can find this is the condition of the strain burst, where your complete rock will be collapsed because of the high stress condition. But if you find the soft rock, Soft rock is not a very genuine term. We can say the hard rock, but basically because of the fracturing, it will be reducing it will be losing its strength. And then in such situation, you will find the problem of squeezing. So if you see the picture at the top, you will find that your tunnel, whatever section it is, because of the fracturing nature and high stress condition, it will be reducing its buckling action, and the whole tunnel will be going inside. And that is a pure case of the squeezing. So these star two are the extreme cases under the high stress condition. If you're rock and these high stresses plus rock condition, it's a club combination of these two natures. So this is basically the squeezing rock reduces the Saint Martin La Porte exercise edit in 2012. This is a work which I found, and the second one is in strange was in a China paper. It's in drainage tunnel in Jingpin hydropower. So I'm not what I explain will be a better judge by the photo as well. Now the question comes that how can we assess the strand burst and rock burst condition? So this is basically I'm taking from the multiple books and literature, that basic concept of the strand burst and rock burst is rock is your massive interlocked highly rock masses. For example, basalt, granite, these kinds of rock are very strongly interlocked and having a less fracture. In this case, there is a chances of rapid release, and that will causing so bursting in massive and highly interlocked rock masses can be triggered as a result of rapid instant release following the rock mass failure or due to the propagation of the strain waves due to the adjacent excavation. Sometimes because of the nearby excavation also, if your ground is competent, that means that if some work is going and your tunnel are excavating and their rock is competent, then definitely the excavation will be same is the situation for the structural features like faults. So seismicity is a very important factor in tunneling or underground works, which is basically rock mass itself. And what I am saying, the basalt and granite, if you saw that such a kind of massive structure is undergoing a fracturing, sudden fracturing, then how much energy will be released in a sudden moment? And that is the concept of strain bursting. So if you find that strain bursting is basically not triggered by a remote event, the following conditions are necessary. So this is the work in Dedrix 2010. In my reference also, it will be there. So Dedrix in 2014 defined the following reason is for strain bursting in tunnel, which is not triggered by the other events. By self, it is triggering. One is the stress concentration. Second is a confinement reduction, because when you are making a cavity, suddenly you will find that you're making a cavity and the rock by nature coming in equilibrium. So we'll make a compressive forces, and that causes brittle fracturing and sudden rapid release of the energy release, by which this complete phenomena will occur. So this is the theory behind the strain burst. The next is so the next is the some empirical work which done by the so many peoples to define the rock burst. Frankly speaking, you just go in these slides and you will find what I'm trying to say. But just in a simple terms, you can understand when your ground is not competent enough in terms of the in situ stresses developed when you are making a cavity, you will find these kind of problems. If your ground is competent enough, and that is the whole concept between the plastic zone and yielding zone. If your ground is weaker as compared to to handling your cavity, then definitely the fracturing zone will increases. If this fracturing will be in a competent rock, then it will be a causes a problem of rock burst. But if it is in a fractured weaker zone, then it will be causing a problem of squeezing. So this is a few work by the Rosnes, Hocken, Brown, Grimstad, and Posnam. It's they are basically the pioneer people who defined these theories and make a complete charting of this information, so that people who is in a practicing will know that whether our ground will be going in such situation or not. So he is defining the sigma c upon sigma theta. Books will be varying in a different manner, but it's sigma theta is nothing. It's the same kind of tangential stresses. So as I am previously told, that tangential and radial stresses are the in situ stresses. So this sigma theta is a basically a representation of the tangential stresses. That is the stresses developed along the boundary, which is invariably termed as in situ stresses. And this sigma c is the strength of the rock in which you are making a cavity. So they suggested that if your sigma theta upon sigma theta will be greater than 4, greater than 7 or 100 into 2.5, then there is a no chances of the spalling or any chance of open joint. And if this will be increasing, that means if sigma c upon sigma theta will be increasing, that will causes issue of your that will cause an issue of your rock busting chances. So this is all about rock busting. Now these are the few photos which I am taking, that how rock busting will occur on a different ground. So if you see, that's a B, C, D is the four. So A is a basically minor rock busting, B is a basically little bit moderate, and then C is basically the C is basically your major one, C and D, and the both are basically in a drill and blast method or in a TBM. So A will be the picture of major rock bust in a TBM drive, and B, C, D is in a drill and blast, which is invariable nowadays. We are called the NATM method. But basically, it's the showing that how the minor, moderate, and D, it's basically indicating the major. So the rock busting phenomena can be, it's a popping action, it's maybe a slabbing action, or it may be the complete collapse of your ground. So these are the some examples of rock bust. Now come to the squeezing, the another response. I must tell you, it is easy to predict rock busting scenario, but it is very difficult to predict squeezing, because as I previously told, the squeezing may be occur in a strong rock because of the large overburden pressure, and squeezing may be occur in a weaker rock because of the large overburden pressure. So to predict the squeezing beforehand, before excavation and design stage or in a tender stage, is a very difficult task. But yes, if you can do this by doing proper geotechnical investigation, you can save so much amount of cost in your excavation. So this is basically the squeezing concept, in which we are squeezing is the ground refers to the weak rock under high stresses. As I am told you, that either the weak rock or the high rock with a fractured zone under high stresses, which causes the rock mass undergo a large deformation, and this action is called as a squeezing action. And the most important part is that this deformation is not sudden, it may be take some time. So that's why it is very difficult to predict as well as assess during the tender time or during the design stages. But it is very important assess to keep these provision in your document, so that there is no chances of variation in the contract document when you are having any kind of understanding that maybe in your ground squeezing will occur. So this squeezing action may result in a damage or failure of the ground support system or require costly re-excavation. Sometimes because of this squeezing action, you have to re-excavate your tunnel profile. That means if you have a dia of 8 meter or 10 meter, you can do the larger excavation, because as I told you, that squeezing is difficult to predict during excavation, and once you are going for excavation and squeezing will occur, then there is no other chance, either you have to re-excavate or reprofiling your structure or giving a heavy support with them. So squeezing ground behavior is identified with a large scale deformation in underground excavation. It may occur not only weak rock mass condition but also observed in hard rock. As I already told you, that it always occur in hard rock with high stresses, and B is a major concern during the construction and conservation of the underground mine opening. So this is one work which done in 2011 by Mercier, Langevin and Hegirgio, which showing that both cases, that in a hard rock with high stresses and a weak rock and a high stresses. So it's a very good work, and you can explore this work by reading this literature. Now the next one is a deformation of underground opening sometimes reach tens of centimeter. As I told you, once squeezing will occur during your excavation, you will find that it will be causing some uncontrolled deformation, and the only thing which is required, you have to re-excavate profile. That means you give a cushion, that whether you will do some kind of extra excavation, so that you give a cushion to ground, that okay, you can deform it, so that at least we cannot give so many uncontrolled support system which may or may not work, because geomaterial is always unpredictable in terms of nature. And that is why Woolley and Andrews in 2015 suggested that in this type of ground condition, stopping deformation is not generally accepted, and the focus should be to control and manage ground movement. Why I am highlighting this clause, sometimes people trying to cater this squeezing ground condition, but as per the concept which is established by the pioneer people, that they suggest and that is why the re-excavation concept or re-profiling concept come in the picture in case of the squeezing ground condition, because the controlled or managed ground movement, it's a most important or critical part in case of a squeezing ground condition. Now, next will be the evolution of the rock mass stability. As I told you, that evolution of the rock mass stability is most difficult part to predict, that how it is squeezing or not, because the deformation of rock mass has happened over a few days, not exactly on the ground. And several empirical methods is already given to assess the squeezing ground condition. And one of the great work, which it's coming in my further slide, done by the Marinos and Hook, which giving some kind of chart, and it will really useful in many of the project. So here the concept will be completely reversed. They don't talk about the sigma C, sigma theta. They talk about the rock mass strength. I just want to put emphasize on one point. Keep in mind there are two terms. One is the intact rock mass strength. That is, we are talking about the uniaxial compressive strength or sigma CM. But sorry, sigma c. But here, in case of squeezing, the critical component becomes your rock mass strength, which is basically sigma cm. So to know this concept, the rock mass strength by the empirical method, there is a certain empirical formulas are available in the books where you can find sigma cm, because sigma cm is not available in the laboratory. In laboratory, you can just check the index properties like sigma c, which is uniaxial compressive strength of the intact rock. But when the things will come into the picture, discontinuity, your rock is become rock mass strength, and this is very important in terms of squeezing ground condition. So when the tunneling is done through squeezing ground, it encounters large deformation and high rock pressure on tunnel support system. So this process is very slow and eventually affect the tunnel opening and damage the support measure designed for normal case and creates instability. So as I already told you, when you're designing your support system, you don't predict the squeezing ground condition. But if somehow it is encountered during excavation, you will feel that, oh, my support system completely collapsed. Now you have to re-excavate the uh, complete profile. You do the more support system. So that has become doubling of your work as well as giving a lot of problems in the contractual conditions. So it is always advisable to keep some cushion in such a manner that you have always provision of such ground condition if it's encountered during your alignments, which will giving a not safety in terms of contract condition as well as give safety to your work as well. Therefore, it is necessary to determine to consider assessment of squeezing condition during design stage of tunnel based on the available geological information to keep the support provision required for squeezing problem. It will not only help in saving large amount of money but also reduce the project progress delay occurred due to the excessive deformation and damage to the support system. And in last, I already told it, the sigma cm is related with the rock mass where the discontinuity is already involved, where sigma c or sigma ca is related to intact rock. That means there is no discontinuity. Now, the work which I am talking about in the previous slide, the basically this work is done by the Hook and Marinos, and it was a really a great work because it's giving us some kind of idea of for the tunnelers or people who work in a caverns and some underground cavities under the high ground stresses. That what will be the basic profiling, that whether it's a minor squeezing, it's a no squeezing, it's a mild moderate squeezing, or some other kind of squeezing. So I am just take us some time on this slide so that everyone, either it's new to tunneling or experienced tunneling, will just to give a first of all the idea behind this concept is in this graph is basically it's considered as an unsupported tunnel. So if your sigma cm upon it, that means the rock mass strength upon in situ stresses. Again, the in situ stresses, that means the stresses developed along the boundary of your cavity, radial and tangential. The ratio of this and the strain, so people will always be confused that strain means the deformity displacement, but basically it's if I am going in a complete context of tunneling, it's basically the ratio of your tunnel closure in terms of your tunnel diameter. That means if your tunnel diameter will be 8 meter and tunnel closure is become yours somehow lesser than the 8 meter or maybe larger than 8 meter, then strain you have to be positive or negative. So on that basis, we are defining the strain. So he is just giving that if your strain will be lesser than 1%, that means tunnel closure upon tunnel diameter will be lesser than 1%. That means you have a no problem of squeezing. Or maybe if squeezing will also come, that is not a hardly issue because you are always allowing your ground to have some kind of flexibility in terms of the moving ground conditions. So very simple support type, very simple tunneling conditions with a rock bolt, shotcrete, and this kind of thing. Again, next is 1 to 2.5%. It is also somehow it is acceptable because we always having some kind of convergence confinement method, and on that basis we can decide that okay, we can allow 1 to 2.5% of tunneling, and then we provide a support. So here the most important part in 1 to 5, the B or C, this corridor is at what time we are providing the support. So the most important part in minor squeezing and that 2.5 in severe squeezing, that where you have to provide your support. So in convergence confinement concept, and this is the basic principle behind the NATAM as well, the new Austen tunneling method, that where at what moment you are providing the support so that you allow the ground which is required, because you don't make a brittle ground so that it will become a extra stress development, and you will not delay in also so that the cavity will for collapse due to the natural pressure. So in case of 1 to 5%, you will be very careful that at what time you are providing the support. And in case of more than 2%, you have to use steel ribs equips as well, which is sometimes called lattice girder and steel sets. But it's below a large debate that whether will we go a heavy steel sets, it's a lattice girder or steel set. But yes, for managing squeezing ground condition, steel sets is one of the very fine work which tunnel people mostly used. Now 5 to 10%, more than 10%. I must say, if these kind of situation will coming, then it is most difficult to face by any person who on the tunnel, whether in the design or in the execution. And most of the tunnel will take time because of these reasons. Uh, because their tunnel will be somehow in a very small stress coming in a 5 to 10% of zone, and that's why they will not manage these things. So they re-excavate the profile, give the yielding supports, allowing the ground to deform, and then will do the further excavation. So these kinds of only alternative will left, along with the four polling, pipe roofing, and some other measures. So this is very important chart to understand the squeezing scenario and what support measure will be taken. And I suggest that everyone who will going in underground deeper ground conditions should keep in mind about these graphs, because it is very important to assess the squeezing ground condition. So this is the work which on that basis what the hook and marinos will do, or maybe you can say that these work will be combination of these works. So this is on different the Indian Society, the International Society of Rock Mechanics, Jetwa, Barla, Armstrong will define on the multiple theories on the concept of the overburden depth, tangential stresses, which is basically in situ stresses, rock mass strength, and the basically sigma cm. So basically considering all three parameters, they will do multiple studies and they will come to the near closure. And if you compare this with the graph which I shown previously, you will found that each and every element will be somehow nearly what basically Hook and Marno says. So in squeezing, these assessment very important in terms of design and executions to know that whether you should go the in squeezing ground condition and what kind of support is required. So just like for example, I'm taking that if your large displacement with convergence, that means moderately squeezing condition. So even in that graph, it is showing the similar kind of 2 to 5%. And here also you will see that the each and everything will be going in a similar kind of pattern. Since here the sigma theta is a numerator, so it's a 2 and 4. Otherwise, if sigma cm is a numerator, then you will find it will be coming 0.4, 0.2, 0.5. So it will be very much in line what multiple theories are saying. So considering one theory, you can be always be available to manage the squeezing ground condition. And I better suggest that in geotechnical investigation phase, we have to be very careful about our investigation, that where the rock burst kind of situation are under high stresses and where the squeezing ground condition under high stresses will occur, so that we can keep our support provision in that manner, so that it will not hamper your project progress as well as not giving any kind of variation during construction design stage. So this is two photos related to the multiple project. I will not quote the name of project because of the multiple reasons. So idea is that this is basically two photos which you're seeing. The first one is a tunnel closure. If you see my pointer, this clear case of complete collapse under the squeezing condition. So it's a basically a good high competent rock. I must say that this rock will be the competent, but because of the fracturing reason, it will be deformed under high stresses. And the second case will be the buckling of your steel set. So this is complete buckling of your steel set. So these situations is prominent. Now, when this kind of situation will occur, you have only two kind of things in your hand. Either you have to re-excavate the tunnel with a larger size, and you have to put a larger support. And these all support which you already previously put on it will become waste for this kind of profile. So again, large costing and further delay. Now the next is ground support under high stress. So it's now what I discussed yet will be a complete summarized here, that how we are managing the ground support. So the three concept which is very important is uniaxial compressive strength of rock mass is an important element of failure initiation. As I already told you, when your ground in situ stresses, that means the stress is developed because of the anthropogenic, because of the excavation. If it will be going in such a manner inside the rock, which is basically the ground existing ground condition, will not making any impact to the longer details. So your plastic zone or yielding zone will be little less, and your ground will be competent enough to cater these kind of problems. So failure initiate at the boundary of an excavation when is exceeded by the stress induced on that boundary. So if your stress induced on the boundary is more as compared to the strength of the rock, then failure will initiate and it will propagate from the initiation to the further stage, and that will further eventually disturb your rock until he will not get the that rock which is more component, which is having a more UCS higher than the induced stresses. So this is the complete phenomena of multiple softwares ground condition, that keep in mind that what will be your strength of the rock and how it will be channelized when you are doing the excavation in terms of your in situ stresses. The most numerical model can follow the similar process of fracture propagation, and this is the level of detailed analysis very important when considering the stability of excavation in rock and when designing support system. More systematic ground support design required in more severe ground condition. As I already told you, if you find during your feasibility stage DPR that maybe you will encounter some severe ground condition, you will be pre-prepared. Either it's a squeezing, swelling, or a high ground the rock burst condition, and accordingly you will design your ground support design in for the highly stressed and highly anisotropic rock masses condition. And in squeezing condition, as I already told you, the timing of the ground support installation is key between the ground support and rock masses, so that you can making such a ground in which you just safely dissipate the stress, because the complete theory of underground is the stress management, that when you provide the support, how you manage the stresses and how you channelize the natural stresses in a natural way by using your ground support installation. So this is one of the work which done by the Hook and Brown in 1980, in which they suggested that if your low stress level and high stress level, and they're giving a multiple support system as well, which is now prevalent in 20 now prevalent till 2025 as well, and they are the pioneer people in case of the in the study of the rock engineering, the Hook and Brown and everything. So if you see that massive rock, that means no jointing, low stress level, then you have a massive rock subject to low in situ stress level, no permanent support is required, and light support, that is a spot bolting or shortcut, will be enough. But if there's a high stress level in the same massive rock, you have to be very careful and provide some kinds of pattern rock bolt or dowels, mesh, shortcut. So even in the massive rock, your support system pattern will be changes by the stress level, and this theory he is applying for jointed rock as well as for heavily jointed rock. So these kind of charts will be become an empirical and guiding method for us when we are designing a port support system. For example, in heavily jointed rock, that means your ground is competent, but your high stress level and heavily jointed rock, then you have to provide some kinds of steel fiber reinforced shotcrete, as well as you have to provide invert struts. If the chances of ground having there, you have to provide invert strut as well. You are reducing the spacing of the ribs or lattice girder. So this is complete theory, what he propound in a different rock type conditions with the high stress and low stress condition. He further with this concept, next is a case study, which I already told you that I will share some kind of case study. And I suggest to every people who at the site or the design, you just read these kinds of concepts, so that you must be aware that if granite is occurred in your site, then and you are sitting on the 1 kilometer below. They're just like a rock burst, similar to slabbing in coarse homogeneous granite. The maximum overburden measure approximately 1.5 meter. So in that Switzerland railway tunnel, they will provide the RB. RB is basically nothing but a rib. As SRB, basically, if SRB I am going, that SRB will be, RB is here. It is clearly radial bolting. Sorry, SRB and SRH will be your steel ribs, and they are basically defining the complete phenomena what they users, so that people will aware that if ground conditions will be encountered, you will find some kind of similar kind of information, you can correlate the things. So these are the few case studies which in a different rail tunnel, roll tunnel, hydroelectric tunnel, where they will found the amphibolite and diorite and granite. So on that basis, they can define the what mitigation measures they adopted, and these case study become a very good understanding that if we are encountering such situation, how we cater. Even we are in a very difficult situation compared to the other ground condition, because our variability of the ground is very much sensitive as compared to them in case of Alps or Andes. But yes, still they suggest some good pathways to us in which we can work and at least safeguard our structure, or if we not safeguard our structure, at least we can having provisions of these, so that when such works will be encounter conditions will be encountered, we can easily do such kind of situation. Similarly for squeezing ground condition, so in case of a squeezing and rocks up, that second is a strain burst condition, the major difference is yielding support. So if you see this kind of a, here you will find one special thing which is basically a LSC, that is basically the yielding support. If you have found the LSC here, it is clearly mentioned about the LSC is basically your some kind of elding bolt. So these are the multiple tunnels in the multiple region: Austria, Switzerland, Venezuela, Austria, Switzerland, where we find such situation. And they are basically deal with these problems with these kinds of support: the rib, steel fiber reinforced shotcrete, some kinds of HD-con elding elements, and double layer LSC is basically there. So they are already defined some kinds of multiple support system in a multiple concept. So it will become a little bit guiding for us when you are catering such situation. And it is always be advisable to keep this as a ready reference, because somehow phyllite is always phyllite. It's encountered in the Indian context or in some other context. So if phyllitis will be occur, that means we should be careful that maybe squeezing ground condition will occur. And in this case, what kind of support will be required? Just take a reference of these kind of literature and keep it in your DPR provisions, so that the large variation and project delay will be safeguard during the construction time. Now that this is a ground management outline. So why I'm keeping this slide, it's basically giving you the complete picture. What we discussed in the previous slides is how we are proceed with these kinds of ground management work. So process to predict and manage rock behavior, that is the most important part in ground management. That means we can predict that what kind of situation will occur in a rock burst or the squeezing, and accordingly we can uh, design a support system. That what will be about support? Either we will go rock bolting, steel ribs, lattice girder, shotcrete, cable anchor, whatever it is. So we have to know that what kind of ground condition will be there, and accordingly we have to modify our support system. So ground control or management is a process to predict and manage rock behavior and failure condition underground opening. The knowledge of ground condition play a considerable role in pillar design, support design, stability analysis of slope, and instrumentation selection and roof control. So I must say via this through this webinar, that the knowledge of ground condition, and I must tell you that civil engineer or rock engineer may be having a not that much knowledge as geologist will have. So you will always make up one good geologist friend. And this is my suggestion to all the people who will works in underground, that you will at least make one or two good geological friends, so that they will always boost your knowledge of ground condition, because that is something is a most critical part in underground engineering, whether it's a tunnel, cavern, road, transport, hydro. You have to be little bit careful about understanding of your grounds in which you are working. And that's why the next point is the geotechnical investigation and ground control management should be carried out during the whole life of project, from feasibility study stage to final commissioning. That sometimes because of the accessibility, you will having a certain knowledge in feasibility stage, then your knowledge will be enhanced in a tender and DPR stage, and then further go on. So its investigation process is not a one go process, it's a keep going process, and accordingly your ground control management is also revising again and again. And principle behind your NATM is also the same thing. We are talking a different names, but the whole concept is lies in second para, that your investigation ground control management will be going from feasibility to commissioning, and accordingly you will revise and think about your ground condition, potential hazard, and determine the type of rock support and reinforcement system in your underground excavation. This is the Thompson 2011 work, in which he is just defining the complete chronology that identify the mechanism of instability, whether it's rock burst, whether it's a strain burst, whether it's a squeezing, swelling, and any other. So first of all, hazard recognition, that how your ground will fail, failure mechanism. Then you can decide that what will be your support demand for these kind of failure mechanism. Accordingly, what will be your ground demand? That means if you're providing this reinforcement, what is become force and displacement on that ground before failure and after support system. Then estimate energy demand. That is basically the concept of strain energy. It's most relevant in case of a component ground condition, that is a rock burst condition. And then select the appropriate rock support. That means if your component strain energy will be large in terms of excavation, you have to provide some kind of yielding support. So selection of the appropriate rock support, reinforcement, its pattern, its installation, and then evaluation of the rock structure under selected ground condition. During the construction also, you can evaluate what your designer proposed the rocket structure. If it is necessary to change these things, modification of the ground support scheme if necessary during construction. So this is the complete philosophy that every construction project below the ground needs to be followed. These are the references which I must say that you everyone just do one time of reading, because it will give you a lot of things to know about this stress management. And this for the practical rock engineering by Abertook is become Bible for the rock engineer people. I must say everyone should keep this in a soft copy. It is available on the Google as well, and read this book, because it will sort out so many problems of the designer as well as on the ground. So I'm intentionally choosing these 9 references, which is really helpful for me during my 16.5 year of experience. And I must suggest that whether it's a starting or at the top level of it, I'm sure they all will all people who will work in underground will be somehow go through these references and document. Thank you. And thank you for listening such a long lecture on this topic of high stresses. Thank you so much.
Thanks, Mr. Rahul, for this wonderful presentation. That was really helpful, and I'm sure that many of you young engineers must have learned a lot. So we are getting some questions on the chat box, and I'll read them one by one, so you may answer them. So Mr. Ratna Kumar is asking that drifting is always not possible to get the principal stresses and their direction. In that scenario, whether the in situ stress is estimated reliable when they are basically conducted by tests in borehole.
Must say that if you having possibility of accessibility, go ahead with the investigation because there is no alternative of investigation. But there is a certain matlab, because I really said this question is coming because I am thought that I will share one insight. There is a world stress map which is available in Google. You can go and you in which area you are working. You will just correlate that area in world stress map where you at least get one idea of the stress regime that in my ground such kind of stress regime will be applicable, and in that way I can think of because uh, and I suggest that each and everyone who will be working in underground, you can push to requirement of the one hydrofracture test or maybe one kind of stress test because actually the stress regime is a very important in underground excavation and somehow in hydro it is followed, but what I found in transportation sector it is missing. So I suggest that if it is a these kind of test will be possible at this, I'll go ahead with the test, and if it is not so, then the only two things which in your hand, one is the regional geology or seismic tectonic graph, which will be available on the GSI or multiple website. So you can just check them. And along with that, there's a world stress map, which is refining each and every year. Okay, so you will go in that map and just find out to stress regime in your area in which you are working. I hope I just take up this query in a way the person wanted. No, the drift is naturally required. If you go into drift, it depends because sometimes if you going inside the very large underground excavation, just in a hydropower sector, if you go in a powerhouse cavern, which will be the large cavity, drift is advisable. But yes, if you have an issue, you can do multiple places borehole and go with that because drifting is required for hydrofracture test. And if you, as compared to borehole, the drifting hydrofracture test and drift will give a more reliable result as compared to borehole. But yes, if you have an accessibility issue, you can try to simulate your result with your simulate your result with a borehole and stress regime available in the literature.
Yeah, thanks. I think one more question we have. Uh, can you elaborate on why it's called strain burst?
Yeah, definitely. If you go in my presentation as well, that basically a strain burst is nothing but a large amount of energy. Because if everything is in equilibrium, it's just a concept of simple. If you consider the granite and basalt rock, which having a less interlocking, that means you have a less joint. So if your competent rock will having a less discontinuity, that means the intermolecular particle between the each and every rock will be closely bonded. And if you trying to disturb by your excavation, definitely the energy. It's a simple example. If you closely bonded something, you need a lot of energy to break. And every action has an equal and opposite reaction. If you break it in a sudden manner, it will be definitely explode in that way. And it's simply strain energy is nothing but the load deformation curve. So you are reducing the load in a sudden moment of time, which causes a large deformation. And then automatically the relation between your stress and strain is just a dissipate within a time bound manner. And that is basically release of large strain energy, what basically inherent between your material. And that's why the rock burst is termed as a strain burst or strain energy burst.
I think we have one more question, one last question that can you elaborate the required additional support conditions in TBM tunneling with regards to geological conditions?
Yes, actually, what happened in TBM, basically, we are not nowadays. It's good sign that few of the project our in Himalayas will be going with the TBM. But in TBM, I always suggest that you have to be more geological awareness as compared to DBM or NATM. So it is advisable to give more of detailed investigation before going into it. So question about the support. In case of a TBM, first of all, the choice of TBM is one of the important concern. So if your ground will be like that monolithic, that monotonous you will go. So you will keep one kind of hard rock TBM. But if your ground is varying, nowadays the EPM TBM will come, which having a tail cutters and a tail sheet and everything. So since in TBM we are basically going in that manner that we will not provide kind of support. But even in the TBM stretches, few stretches will come in that way where you manually excavate, go ahead, and then your TBM will mobilize. There is a certain cases in Himalayan region in hydropower projects will coming where where we are aware of that people will move TBM, but in certain stretches they will use DBM so that their TBM can be mobilized. So if such scenario will be coming, then definitely you have to use fundamental support system of your drill and blast methods on atom, and then you move at TBM. Otherwise, in case of a TBM, either you can go with the EPV TBM, or that the choice of TBM itself is basically important parameter to know the right ground condition. Because if your ground is different and you choose your TBM different, then your TBM will definitely stuck somewhere and you will found difficulty. So three things is most important TBM tunneling. One is geotechnical investigation. More aware geotechnical investigation is principal requirement when you deploy an TBM in your underground cavity. Second thing, you should know that what kind of ground will cater. That means if in case of any kind of ground which is coming in the TBM, which will be in a small stretch, then you have to know that, okay, we will go with a manual excavation for this stretch and then our TBM will go ahead. So it's not such a kind of thing that any specific support system, it's all depends your ground condition in which you are mobilizing your TBM.
Thank you, Rahul sir. I think we are done with the Q&A. I can't see any more questions. So thank you for the wonderful webinar covering detailed design aspects and the case studies. I'm sure that your experience will be very useful for everyone. Just for everyone's knowledge, I would like to inform that our past webinars are also available on our YouTube channel. And this webinar, after getting necessary permissions from the speaker, will be uploaded shortly. And if you are not a member of TAIym and want to become one, kindly contact us